All right, in this video, we're going to talk about section 5.2, dealing with definite intervals. And out of that section, we're going to be sketching the graph of the curve and approximating the net area using Riemann sums. Also, we use geometry to find the area and net area of a described region. Also, we'll write definite intervals from the limits of sums, and we'll evaluate definite intervals using properties of definite integrals and use the limit definition of the definite integral to evaluate definite integrals. All right, so back in section 5.1 in a previous video, we introduced Riemann sums as a way to approximate the area of the region bounded by the curve y equal f of x and the x-axis on an interval, a closed interval from a to b. Okay, so now we're going to discover the geometric meaning of Riemann sums when f is negative on some or all of the closed interval AB. Once this matter is settled, we'll proceed to the main event, which is to define the definite integral. And with definite integrals, approximations given by Riemann sums become exact. Okay, so first of all, let's talk about what net area is by definition. So the definition of the net area would be this. Let's say we consider the region R bounded by the graph of a continuous function called f and the x-axis between x equals a and x equals b. The net area of R is the sum of the areas of the parts of R that lie above the x-axis minus the area of the parts of R that lie below the x-axis on the closed interval a to b. So here's an illustration of just that. We have the graph of y equal f of x, and we have the closed interval a to b, and we're dealing with this function and the x-axis. So here's the x-axis here. Now, as you can see here, these green shaded areas between a and b, that's going to be the area that's above the x-axis. And this area down here is orange. That's going to be minus that area that lies below the x-axis. So it's going to be these two being positive areas. The one on the below the x-axis will be your negative areas. Okay, so that's basically what net area is. All right, so let's talk about example 1. And this is back when we were doing Riemann sums in section 5.1. or approximating the area under the curve. All right, let's say the following function is negative on the given interval. And here we got f of x is equal to negative 6 minus x cubed, and the interval is from 2 to 7. Part A, you're to sketch the function on the given interval, and part B, approximate the net area bounded by the graph of f and the x-axis on the interval using a left, right, and midpoint Riemann sum with n is equal to 5. Okay, so the first thing we need to do here, now here you're given a choice of graphs, so you have to select which one will fit the one that's on the calculator. So if I go here, let's do y equal to, let's clear this equation out, and then I'm going to type in the negative 6 and then minus x cubed, x c theta n for the x, hat key, and then 3. Right arrow to get out of it. All right, so now let's pick our window here, set our window here, go to window. And if I'm looking at this, I'm pretty much going to be going from negative 12 to 10. Let's do that. Let's try that one. Negative 12 for the x-min. X-max will be 10. And I'm going to leave the x scale at 1. I'm sorry. Let this be 0. X-min will be 0. X-max will be 10. X scale will be 1. But for the y-min, let's try from negative 360. And then y-max will be up to negative 12. And I'm going to say the x scale will be in increments of 10. and then press graph and see what happens. Well, pretty much you can see what's going on. On that interval, with this selected window, it's going downwards. So if you look at the choice of graphs, it's obvious it will have to be answer A. So A would be the correct graph to choose. Okay. So that's part A. Part B is on the next page, is where we're going to find the approximate net area using the left Riemann sum, and then the midpoint Riemann sum, and then the right Riemann sum. Okay, so in this case, I'm going to do this on a separate sheet of paper because I don't think I have enough space on here, so let me grab a separate sheet. We're going to start with the left Riemann sum, but let's identify what we already have. We got the interval, which is going to be from 2 to 7. And n, in this case, is 5. So here I can find out what delta x is. That's going to be b minus the a divided by n, upper limit minus the lower limit divided by the number of subintervals. So this is 7 minus 2 divided by n, which is 5. 7 minus 2 is 5, so 5 divided by 5 will be 1. So the lengths of my subintervals will be 1. That's delta x. And what would be my subintervals? Since n is equal to 5, I must have 5 subintervals, each with a length of 1. So these are my subintervals here. I'm starting with 2. So I add 1 to that, that's going to be 3, so it'll be from 2 to 3. The next one will be from 3 to 4. The next one will be from 4 to 5. The next one will be from 5 to 6. The last one will be from 6 to 7 because my endpoint, right endpoint, is at 7. So those are my 5 subintervals. All right, next I'm going to find the left Riemann sum. Okay. And the way we do that is, of course, we do delta x times f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4. The left Riemann sum, we look at our left endpoints for each of these subintervals here. So these are my left endpoints for each of these 5 subintervals. The 2, 3, 4, 5, and 6. And delta x is 1, so it'll be 1 times f of x sub 0, which is 2, plus f of x1, which is going to be 3, plus f of x2, which is 4, then f of x3, which is 5, plus f of x4, which is 6. Okay. Now my function in this case is that f of x is equal to negative 6 minus x cubed. So let me go ahead and write that here. F of x is equal to negative 6 minus x cubed. And of course, if I look at y equal to, that's what I have here. Now, what I want to do here is ask the calculator what values of y will be when I put in those x values. So here, I'm going to go to second table set. You want to make sure that you're under the independent ask is highlighted. In case it isn't, if you got your screen looking like this, after pressing second table set, what you want to do is use your down arrow key to independent, go to right arrow, and press enter to highlight the word ask. okay? Because you want the calculator to ask you what values of x that you need for that function f of x equals negative 6 minus x cubed. All right? Then I'm going to go to second table. Now, if you have anything in this table, you want to press your delete key. Delete everything out to clear that whole thing. Now, under the x column, that's where I'll put in these values for x. And that will give me my f of x values here. And here I'm starting off with 2. So here if I let x equals 2, type in 2, that'd be negative 14. X equals 3, type that in, I'll get negative 33. Type in the 4, you get negative 70. Type in the 5, you'll get negative 131. Type in 6, you'll get negative 222. Okay, so let me go and put those in. So here I got 1 times f of 2 was negative 14, plus f of 3, that was negative 33, f of 4 was negative 70, f of 5 was negative 131, and f of 6 was negative 222. Okay, now I'm going to add up these numbers together. So here's what I'm going to have. Let's see. I'm going to do second mode to get out of this. But here if I do negative 14 plus negative 33 plus negative 70 plus negative 131 plus negative 222, hit enter, I'll get negative 470. So now my delta x is still going to be 1 times negative 470, which ends up being negative 470. So my approximate net area using the left Riemann sum would be negative 470. Okay, that's the left Riemann sum. Now for the midpoint Riemann sum, this time it's going to be delta x. Well, actually, I know what delta x is. I can just say delta x is going to be equal to 1. So I can just say 1 times f of each of these. I have to find the midpoint of those. So like in this case here, for 2 and 3, if I add 2 and 3 together, I'm going to get 5. 5 divided by 2, that's 2.5. For 3 and 4, 3 to 4, 3 plus 4 is 7 divided by 2, that's 3.5. And then for 4 to 5, 4 plus 5 is 9 divided by 2, that's 4.5. And then from 5 to 6, 5 plus 6 is 11 divided by 2, that'd be 5.5. And then 6 plus 7 is 13 divided by 2, 6.5. Because those midpoints, that's halfway between those endpoints of each of your sub-intervals here. So I'm going to use those midpoints to evaluate the midpoint Riemann sum. So this will be f of 2.5 plus f of 3.5 plus f of 4.5 plus f of 5.5 plus f of 6.5. So now I get 1 times. Let's find out what this value is at 2.5. So I'm going to go to second table, because I've already got got everything in the calculator. So I'm going to press delete. And let's start with 2.5. Type in 2.5, you get, now in this case, I need to put the cursor on top of this, so this will be negative 21.625. Because this calculator that I'm using only goes out to 2 decimal places. And I need all the decimal places I'm going to need to come up with the exact answer. Now I'm going to go back to under the X column, type in 3.5, hit enter. Let's see what that exact value would be, negative 48.875. Plus, and then down arrow left, 4.5, type that in. I'm going to use my up arrow and go to the right. It'll be negative 97.125. And then f of 5.5, type in 5.5 underneath the x. This will be exactly a negative 172.375. And then finally 6.5. That's negative 280.625. So now I got 1 times. Then I'm going to add up all those negative values together. Okay, so if I pull this up, and by the way, feel free to pause the video if you need to. Let's see, negative 21.625 plus negative 48.875 plus negative 97.125 plus negative 172.375 plus negative 280.625. This will give me negative 620.625. And of course, 1 times negative 620.625 would be negative 620.625. That represents the area for the midpoint Riemann sum. So the approximate net area using the midpoint Riemann sum, that's negative 620.625. And now for the right Riemann sum. My delta x is still going to be 1 times. Now we look at our right endpoints here from each individual sub interval. So the ones I'm going to use purple arrows to show you your right Riemann sums are 2, 3, 4, 5, 6, and 7. The ones in purple are the right Riemann sum, right endpoints for your right Riemann sum. So I got 1 times f of 3 plus f of 4 plus f of 5 plus f of 6 plus f of 7. Okay. And I've already got the f of x equal to negative 6x minus 3 in the calculator. And I've already have it programmed to ask for my x value. So we'll do second graph for the table. And I'm going to delete all of these by pressing the delete button, or DEL. Some of these I've already have. So like for f of 3, that's negative 33. F of 4, negative 70. F of 5, negative 131. F of 6, negative 222. But for f of 7, I'll need that. That's going to be negative 349. So I got negative 33 plus f of 4, that's negative 70, plus f of 5, that's negative 131, plus f of 6, that's negative 222, plus f of 7, negative 349. So 1 times if I add negative 33 to negative 70 to negative 131, to negative 222, add that to negative 349, you will get negative 805. So I have 1 times negative 805, which will be negative 805. So that is going to be the approximate net area for the Wright-Riemann sum, if I was using that. So using the Wright-Riemann sum, the approximate net area will be negative 805. Okay. Okay, so that was example 1. Here we had to use all 3. The left, the midpoint, and the Wright-Riemann sums. All right, next is the definite integral. We'll talk about that. Now, what Riemann sums for the function f on the closed interval AB does, it gives us approximations to the net area of the region bounded by the graph of f and the x-axis between x equals a and x equals b. But the question is, how can we make these approximations exact? Well, if f is continuous on the closed interval AB, it is reasonable to expect the Riemann sum approximations to approach the exact value of the net area n as the number of subintervals n approaches infinity. So that means if you let your number of subintervals get bigger and bigger and bigger, then we're going to get closer and closer and closer to the exact area. So pretty much this illustration has this. Here in this case, they write this in terms of limits as the net area equaling to the limit as n approaches infinity of the summation for k equaling from 1 to n of f of x star sub k times delta x. And here's an illustration of just that. And as the number of subintervals n increases, then the Riemann sum approaches the net area of the region between the curve of y equal f of x and the x-axis on the interval from a to b. Okay. And this continues on to what they call a general partition of AB, and that consists of n subintervals. Now, what we've been doing with Riemann sums, it involves regular partitions on which the subintervals had the same length, called delta x. In this case, our lengths in this case are not necessarily going to be the same as illustrated here in this picture. And the definition for a general Riemann sum would be this: suppose that x0, x1, x1, x2, and so on, all to x of n minus 1 to x of n are subintervals. And we let delta x of k be the length of the subinterval, and let x star sub k be any point in that interval. Okay? So it's going to look like this, and then it is defined as the sum of the summation from k equaling from 1 to n of this expression. Now notice our delta x's do not have to be the same. They don't have to be of equal length. So here we call that the general Riemann sum for f on the closed interval a to b. All right, and then our next definition would be the definite integral. Here we're going to let f be defined on the closed interval ab is integrable on the interval ab if the limit as delta approaches 0 of the summation for k equaling from 1 to n of f of x star sub k times delta x sub k exists and is unique over all partitions of AB and all choices of x star sub k on a partition. This limit is called the definite integral from a to b of the function f. And we write it like this: the integral from a to b of f of x dx That's going to be equal to the limit as delta approaches 0 of the summation from k is equal to 1 to n of f of x stars of k times delta x of k. That's just a definition of what the definite integral is. Now, there is a direct match between the notation on either side of the equation of this definition, as you can see. Notice that we're using the integral sign. That also means a sum. So does this summation right here. This Greek letter sigma means a sum. Also, we have our upper limit, which is the one on the top, and the lower limit of integration that's on the bottom. So we're going from A to B. Lower limit to upper limit. Same thing here. Lower limit is on the bottom, the upper limit is on the top of that sigma notation. And then you have your integrand, f of x. Same thing here, f of x star sub k. And then you got dx, and we also have delta x in our sigma notation. Okay, so pretty much you can see the direct match between those two. And of course your x is going to be the variable of integration in this illustration. Okay, next we'll look at evaluating definite integrals. And theorem 5.2 says this for integrable functions. If f is continuous on the interval ab or bounded on ab with a finite number of discontinuities, then f is integrable on that interval ab. So here's just an illustration of just that. And as you can see here, the net area is the integral from a to b of f of x dx. That's going to be the area above the x-axis, and in this case, it's going to be these green regions here, 1 and 3, minus the area below the x-axis. And as you can see here, region 2, that's in orange, that's below the x-axis. So we have to subtract that from the sum of those two. All right. Now we can identify the limit of a sum. So what we're going to be doing here in this case is just writing it in as a definite integral. Let's assume that the limit as delta approaches 0 of the summation for k equaling from 1 to n of 3x star sub k squared plus 2x star sub k plus 1 times delta x of k is the limit of the Riemann sum for the function f on this interval, 1 to 3, that's given to you, the interval from 1 to 3. Identify the function f and express the limit as a definite integral. What does a definite integral represent geometrically? Okay, well in this case here, I want you to think about this for a moment here. That x sub k star, or x star sub k I should say, those are just going to be your x's. So this x star sub k there, that represents an x. X star sub k again represents the x. This right here, that delta x of k, that represents dx. So if we were to write this as a definite integral, we use our integral sign here. Excuse me. Now the interval we're using is from 1 to 3. So the lower limit goes on the bottom, the upper limit of 3 goes on the top. From 1 to 3, the low to high, of, instead of the x star sub k, we use x. So it would be 3x squared, 3x and that's squared, plus 2x, and that's going to be just 2x, plus 1. Instead of delta x of k, dx is what we use. And that's all we have to do in that problem, because they just want the expression of the limit as a definite integral, and this is it. Now, what does that definite integral represent geometrically? That actually represents the area of the curve, of this curve, or the area of the region of this curve from 1 to 3. Okay, that's basically what that definite integral represents if you were to do this geometrically. Example 2, let's say we want to consider the following limit of Riemann sums of the function f on a to b. Identify f and express the limit as a definite integral. So here's where we got the limit as delta approaches 0 of the summation for k equaling from 1 to n of x star sub k raised to the 7 times delta x sub k. And our interval is from 3 to 7. Well, this right here would be your x, and this represents dx. So if I was to write this as an integral, it'll be from the integral from this notation, or this interval notation, 3 to 7, 3 to 7, of, this will be x, and it's raised to the 7, so it'll be x to the 7 times dx. That's all there is to it. So it'll be the integral from 3 to 7 of x to the 7th dx. Okay. All right, and here's one more of these. We got the limit as delta approaches 0 of the summation for k equaling from 1 to n of x star sub k, sine of x star sub k, delta x sub k. And the interval is going to be from 2 to 3. We want to identify the function and express this as a limit, express this limit as a definite integral. Express the limit as a definite integral, so it'll be the integral from, now we're going from 2 to 3, so the 2 has to go in the bottom, the upper limit is on top, 2 to 3. This represents x, and this is going to be x. That represents dx. So it's just going to be x times sine of x, then delta x sub k would be dx. Okay. Okay. All right, next we'll evaluate definite integrals using geometry. There are some times that we can use familiar area formulas to evaluate integrals. So like in example 4, we got this. We want to graph the following function and then use geometry instead of Riemann sums to find the area and the net area of the region described. So here we got the region between the graph of y is equal to the absolute value of x minus 2 and the axis 4, x is greater than or equal to negative 3 and less than or equal to positive 3. All right, so in this case, I'm going to pull up a separate sheet of graph paper and then try to graph y equals to the absolute value of x minus 2. And we're going from negative 3 to 3. Now, if you want to, you can do a xy coordinate plane and then go from negative 3 up to 3. Okay. So in this case here, if x is negative 3, absolute value of negative 3 is 3. 3 minus 2 is 1. For x equals negative 2, absolute value of negative 2 will be 2. 2 minus 2, 0. For negative 1, absolute value of negative 1 is 1. 1 minus 2 is negative 1. X being 0, absolute value of 0 is 0 minus 2, that's negative 2. And then for x equals 1, absolute value of 1 is 1 minus 2 is negative 1. For 2, absolute value of 2 is 2. 2 minus 2 is 0. And finally, absolute value of 3 when x is equal to 3 will be 3. 3 minus 2 is 1. So these are my points that I would use to make the graph of that absolute value function. So in this case here, -3 and up 1, -2, 0 on the x-axis, -1, -1, 0, 2, 0, -2, then 1, -1, 2, and 0, 3, and 1. So we have that familiar V-shaped graph where it is shifted down 2 places. Okay, and I'm going to restrict this from -3 to 3. But in this case here, if you were to look at this graph and the choices of graphs that they give you, this will have to be graph D. So graph D represents the graph of the function y is equal to the absolute value of x minus 2. Now we want to find the area of the region and then the net area of this region. Now we're only going from -3 to 3. Okay? So we're restricted from -3, that's to the left, and +3 to the right. And the x-axis and the graph itself. So what I'm going to do here is shade in the area that's bounded by my endpoints and the graph and the x-axis. Here's one area right here, and here's another area right here on this end, because here's the x-axis right here. And then I have another area that's going to be, in this case, here's the x-axis and here's the graph. That's this area as well. Notice that this area is below the x-axis. Below the x-axis. And these two that are in dark blue are above. All right, so this I will label as region 1. This I will label as region 2. This one on the bottom, I'm going to label that as region 3. Each one of those regions, I'm going to find the area. All right, and by looking at this, that figure, that geometric figure is a right triangle. And in a right triangle, the area formula for that, area for region 1, the area of a right triangle is always 1/2 the base times the height. All right, so the base is going this way, height goes straight up and down. The base has a distance from -2 to 3. That distance is only 1. So I have 1/2 times the base, which is 1, and then this height right here, from 0 up to 1. That distance from 0 to 1, that's my height. That's going to be 1. So 1/2 of 1 times 1 ends up being 1/2. So the area of that region there will be 1/2. And region 2 over here, same thing. From 2 to 3, that base is 1. From 0 to 1, that height is going to be 1. So the area there of that triangle is 1/2 the base times the height, or 1/2 of 1 times 1, which is 1/2. Now, for this one that's in blue, and I'll label that as region 3. Well, it is a triangle, so I'm going to use 1/2 the base times the height. And here I can use that because if you notice, here's my base, from -2 to 2. That distance is from -2 to 2. That's going to be 1, 2, 3, 4. That base is 4, so it'll be 1/2 of 4 times this height. This is from 0 up to -2. That distance from 0 to -2, that's going to be 1, 2. So 1/2 of 4 times 2, well, 1/2 of 4 is 2. 2 times 2 will be 4. So region 3 has an area of 4. So now the area itself and they're asking for the area of the region is going to be this. The sum of those three regions, R1, R2, and R3. So region 1 has an area of 1/2. Region 2 has the area of 1/2 as well, plus region 3 that has an area of 4. So 1/2 plus 1/2, that's 1 whole, plus the 4 will give you 5. So the area of the region, that adds up to 5. Now they want the net area of the region. Here's how we find the net area of the region. That would be the area, the sum of the area, that's going to be the sum of the area that's above the x-axis minus the sum of the area that's below the x-axis. Here I got two areas that are above the x-axis, R1 and R2. But R3, if you look at R3, it is below the x-axis. So I have to say negative the area of R3, or region 3. Well, R1 was 1/2, plus R2, that's 1/2. But this time R3 was 4, but it's below the x-axis, so it has to be negative 4. And then we add those together. 1/2 plus 1/2 is 1. 1 plus negative 4 is negative 3. So the net area of this region will be negative 3. Okay, here's the next example. Let's say we got y equal 3x minus 9. And I want to use geometry to find the area and net area of the region described. Now, in this case here, I did use Desmos, as you can see here, to graph this. Okay, and they tell you the region between the graph of y equal 3x minus 9 and the x-axis from -1 to 7. So here's -1 over here. There's 7 right here. And this is the graph of y equal 3x minus 9. Based on that, you can see that it will have to be, if you looked at the choices of answers, or choices of graphs, it will have to be D. Because notice that this graph is crossing the x-axis at 3. Okay. Now we can find the area of the region in square units. All right. Now we're bounded by the interval from -1 to 7, the x-axis, and the graph of this line. So the shaded area that I'm going to be focusing on is this right here. And here I'm using yellow to highlight this. So that's the area bounded by this linear equation, the x-axis, and my endpoints from -1 to 7. And then next, the other one will be this one. That's above the x-axis and the line. And of course, up to 7. Okay. So that's going to be the area that we're talking about here, of both of these. And they're both triangles, as you can see. In fact, they're going to be right triangles. So, in this case, I'm going to let this be R1, and this one be R2 up here. So the area for region 1, since it's a right triangle, that's going to be 1/2 the base times the height. Okay? My base goes straight across, the height goes up and down. From 3 to -1, if you go over from -3 to -1, that's going to be 1, 2, 3, 4. That base has a length of 4. The height going straight up and down, and this is from 0 up to, and in this case this might be hard to see, it's from 0 to 12, because at -1, if you did -3 times the -1, that's going to be -3. 3 minus 9 would be -12. So it has a height of 12. And we're using positive here. And by the way, this graph, this line, is y is equal to 3x minus 9. All right, so now let's find the area. Half of 4 is 2. 2 times 2, 2 times 12 will be 24. So this region, number 1, has an area of 24. Now for this region here that's in green, that's also a triangle, and it has the area of, we can find that area by taking 1/2 the base times the height. So this is 1/2. From 3 to 7, that's 4. That base is 4. The height at 7, well, 3 times 7 was 21. 21 minus 9 would be 12. So the height there is at 12. And you can see here, half of 4 is 2. 2 times 12 is 24. So this area that's in green is going to be 24 square units. Now for the area, it's going to be the sum of the two regions, R1 plus R2. So that's 24 plus 24, which is 48. So that means here that the area of the region is 48 square units. Now for the net area. For the net area is this. The area below the x-axis will be negative. So R1 is below the x-axis. That's in yellow. That's going to be negative R1 plus the area that's above. R2 is above, so it would be negative R1 plus R2. Well, R1, we found that out to be 24, so that's negative 24 plus R2, we found that out to be 24. Negative 24 plus 24 is 0. So the net area here would be 0. Net area of the region is 0. Okay. All right. Now let's look at the definite intervals from the graphs. Let's say the figure to the right shows 4 regions bounded by the graph of y equal x times sine of x, R1, R2, R3, and R4, whose areas are 1, pi minus 1, pi plus 1, and 2 pi minus 1, respectively. And we want to use that information to evaluate the following integral. So here we got the integral from 3 pi halves to 2 pi. Of x times sine of x dx. All right, we're going from 3 pi halves to 2 pi. So here's 3 pi halves here, and 2 pi is here. So we only got like one area here, and that's R4. But R4 is below the x-axis, so that means it will be negative of R4. R4 is negative because it's below the x-axis. And R4 was 2 pi minus 1, so we bring over the negative sign. And R4 was 2 pi minus 1. Well, if I distribute the negative, it would be negative 2 pi minus a negative times a minus 1 would be plus 1. Another way of writing that would be 1 minus 2 pi. Okay. All right, and that's all there is to it with that problem. Okay. Example 7 looks like this. The figure to the right shows the area of regions bounded by the graph of f and the x-axis. Evaluate the following integral. So in this case here, we have the integral from 0 to a of the function f of x dx. The integral from 0 to a of f of x dx. Here's 0 here. A is right here. And we only got one region here between 0 and a, and that's this one. And it's above the x-axis. So the integral from 0 to a of f of x dx will end up being 12. Okay. But suppose you had something like this, and I'm making this one up right here. The integral from a to c. Or better yet, from 0 to c. Let's say that. Integral from 0 to c of f of x dx. So now in this case, here's 0 here, and c is way over here. 0 to c. That means we need to include the area of all three of these. That 12, this area here, that's a positive, so it would be positive 12, plus, now the 8, this area is below the x-axis, so that 8 will become negative 8, plus this area that's above the x-axis, that's the 13, so it will be positive 13. So if I add 12 and negative 8 together, that would be 4. 4 plus 13 would be 17. So the integral from 0 to c of f of x dx would end up being 17. Okay. All right, next we'll look at the properties of definite integrals. The properties of definite integrals. So here's the definition. One is for reversing limits and the other one is identical limits. Suppose f is integrable on the interval a to b. The first one is this. If I have the integral from b to a of f of x dx, I can swap these limits in their positions, but I have to include the negative sign. So the integral from b to a of f of x dx will be the opposite of the integral from a to b of f of x dx. Okay, we can just swap the limits here, but we need a negative sign in front of it. And number 2, the integral from a to a of f of x dx, that's going to be 0. So if your lower limit and your upper limit are exactly the same, then its integral will be 0. Okay. And now, next we have the properties of definite integrals here. The first two are the exact same that I just got through talking about by definition. Integral from a to a of f of x dx is going to be equal to 0, and the integral from b to a of f of x dx will be the opposite of the integral from a to b of f of x dx. Those are definitions here. And that's if I let f and g be integrable functions on an interval that contains a, b, and p. Now, number 3 is pretty much the sum and the difference of 2 or more integrals here. Of 2 or more expressions if I'm taking this integral. The integral from a to b of f of x plus or minus g of x, Well, I got the integral of the sum. I can write that as the sum of the individual integrals. Same holds true for the difference here. The integral from a to b of f of x dx plus the integral from a to b of g of x dx. And then number 4 is that constant multiple rule, the integral from a to b of c times the function f of x dx. I can pull the constant out in front, so it'll be c times the integral from a to b of f of x dx for any constant called c. Now number 5, I have the integral from a to b of f of x dx. That's going to be this. Let's say p is involved. The integral from a to p of f of x dx plus the integral from p to b of f of x dx. This upper limit has to be the first one has to be the same as the lower limit of the second for you to do this, or use that property. And then number 6, the function absolute value of x is integrable on an AB, and the integral from a to b of the absolute value of f of x dx is the sum of the areas of the regions bounded by the graphs of f and the x-axis on a to b, on the interval a to b. Okay. Now we're going to use some of these properties that we got through talking about here in table 5.4 with these examples. Let's say the functions f and g are integrable and the integral from 2 to 7 of f of x dx is equal to 8. The integral from 2 to 7 of g of x dx is equal to 4, and the integral from 5 to 7 of f of x dx is equal to 3. Evaluate the integral below or state that there is not enough information. All right, so in this case, let's say we have the integral from 2 to 7 of 3 times the f of x minus 2 times g of x dx. All right, now let's see here. I'm going to have to use the difference rule here by breaking this up as the difference of the individual integrals here. So this will be the integral of, this is the integral from 2 to 7, 2 to 7, of 3 times f of x dx minus the integral from 2 to 7 of 2 times g of x dx. And then next, use that constant multiple rule on each of these. I can pull the 3 out in front, so it'll be 3 times the integral from 2 to 7 of f of x dx minus, pull the 2 out in front here, it would be 2 times the integral from 2 to 7 of g of x dx. All right, and now the next step would be this, using these given integrals. The integral from 2 to 7 of f of x dx, I have that right up here. That's going to be equal to 8. So I have 3 times 8 minus 2 times the integral from 2 to 7 of g of x dx. Well, I have that right here. Integral from 2 to 7 of g of x dx, that's going to be equal to 4. And then the next step would just be simplified. 3 times 8, that's 24. Minus 2 times 4, that's 8. 24 minus 8 would be 16. So the integral from 2 to 7 of 3 f of x minus 2g of x dx will be 16. Okay. Okay, now example 9. Here we're going to use only the fact that the integral from 1 to 6 of 3x times the quantity x minus 8 minus x dx is equal to 205, and the properties of integrals to evaluate the integrals in parts A through D, if possible. In part A, we want to choose the correct answer below, and if necessary, fill in the answer box to complete the choice. And in this case here in part A, we got the integral from 6 to 1. Integral from 6 to 1 of 3x times the quantity 8 minus x dx. Well, notice I almost have this up here, but notice that the 1 is on the bottom and the 6 is on top, so I need to switch these limits out. If I do that, I need to put a negative sign in front, so it'll be negative of the integral from 1 to 6 of 3x times 8 minus x dx. Well, this is exactly this right here. So the integral from 1 to 6 of 3x times the quantity 8 minus x dx is 205. So here I'm going to have a negative 205 as the final answer. Okay. Are there any questions about, well, if you have questions about it, feel free to reach out to me by email. All right, part B, the integral from 1 to 6 of 8 of x times the quantity 8 minus x dx. So let's see here. Well, this is almost this, but what's missing here is the 3. Well, if I want that a 3 to be there, what I can do is I can put a 3 here. However, to compensate for that, I have to multiply it by its reciprocal. So the reciprocal of 3 will have to be 1/3. Okay? For that, I can put a 3 here, but to compensate for that, I have to write it with a 1/3. It's reciprocal. Okay? Because if I take 1/3 and multiply it by 3, I will get this back. So this is just another way of rewriting it. That way, I can find out what the integral of 3x times at 8 minus x dx from 1 to 6, which is what I have here. That's 205. But then I got the 1/3 out in front, so it'll be 1/3 times 205. And this will be 205 divided by 3. And I'll leave that as an improper fraction. Okay. All right, part C looks like this. We got the integral from 6 to 1 of 6x times the quantity 8 minus x dx. Notice the bigger numbers on the bottom, the smaller numbers on top. I need to change it to where the smaller numbers on the bottom and the larger numbers on top. So I need to flip these and then put a negative sign in front. So it'll be negative times the integral from 1 to 6. Something else I can do here. That's 6x. I got 3x up here. 3x times what number would give me 6x? And it will have to be a 2. So it'll be 2 times 3x times 8 minus x dx. And notice I can pull the 2 out in front with this negative sign. So I'm going to have negative 2 times the integral from 1 to 6 of 3x times 8 minus x dx. And in this case, that integral from 1 to 6 of 3x times the quantity 8 minus x dx, that is, and I forgot my negative sign, so it'd be negative 2 times, that is going to be 205. And negative 2 times 205 would be negative 410. Okay? So the integral from 1 to 6 of 3x times the quantity 8 minus x dx, that's the 205, but I got negative 2 out in front, so it'll be negative 2 times that would be negative 410. And part D, here we got the integral from 1 to 12 of 3x times the quantity 8 minus x dx. Notice from 1 to 12. I only got from 1 to 6. So if I was to break this up, this would be the integral from 1 to 6 of 3x times 8 minus x dx. Plus the integral from, help me out, from 6 to 12 of 3x times the quantity 8 minus x. And I need a dx here and a dx here. I know what this is, that's the 205, but I know nothing about the integral from 6 to 12 of 3x times the quantity 8 minus x dx. So, based on that information, I cannot calculate this integral, because I know nothing about the integral from 6 to 12 of 3x times 8 minus x dx. Okay? All right, take a look. Let's look at example 10. Let's say we got this. The integral from 2 to 4 of f of x dx is equal to 6. The integral from 2 to 7 of f of x dx is equal to 4. And the integral from 2 to 7 of g of x dx is equal to negative 7. And I want to evaluate these integrals here. All right, so we'll start off with the integral from 7 to 2 of g of x dx. Now notice that the bigger numbers on the bottom and the smaller numbers on top. I need to switch these limits. So it'd be the integral from 2 to 7, but I need a negative sign in front of that if I'm going to do that, of g of x dx. Well, the integral from 2 to 7 of g of x dx, if you look up here, that's the negative 7. So let me bring this negative over. The integral of this part is negative 7. So negative of a negative 7 is 7. Okay. So I have to use the properties here of integrals. So flip the limits over and put the negative sign in front. And then the integral from 2 to 7 of g of x dx is negative 7. So negative of negative 7 is 7. All right, the next one is the integral from 2 to 7 of 3 times g of x dx. Well, using the constant multiple rule, I can pull the 3 out in front, so it'll be 3 times the integral from 2 to 7 of g of x dx. So at 3 times the integral from 2 to 7 of g of x dx, that's your negative 7. So 3 times negative 7 is negative 21. And then the integral from 2 to 7 of g of x minus f of x dx, g of x minus f of x, that's dx. Well, I got the difference, well, the integral of the difference, I can write that as the difference of their individual integrals here. So this would be the integral from 2 to 7 of g of x dx minus the integral from 2 to 7 of f of x dx. Well, in this case here, integral from 2 to 7 of g of x dx, I have that here. That's negative 7. Minus the integral from 2 to 7 of f of x dx. Here's 2 to 7. F of x dx, that's 4. So I got negative 7 minus 4, which would give me negative 11. Okay. And the integral from 2 to 7 of 3 times g of x minus f of x dx. And I'll go ahead and break this apart and use the constant multiple rule. That 3 in front of the g of x can go on the outside. So it'll be 3 times the integral from 2 to 7 of g of x minus the integral from 2 to 7 of f of x dx. And I also forgot the d of x here with that dx with g of x. So this should be g of x dx minus that. So now I have 3 times the integral from 2 to 7 of g of x dx. That's a negative 7 minus integral from 2 to 7 of f of x dx. That's going to be 4. 3 times negative 7 is negative 21, and negative 21 minus 4 ends up being negative 25. So the integral from 2 to 7 of 3g of x minus f of x dx will end up being negative 25. Okay, and here we're going to use the value of the first integral, I, which is this, the integral from 0 to 3 of x cubed minus 4x dx equaling to 9/4. I'm going to use that to evaluate the two given integrals here. So in part A, we got the integral from 0 to 3. Integral from 0 to 3 of 8x minus 2x cubed dx. All right, in this case here, let's see what we can do here. There's a common factor in these two terms I can factor out. And I can make it look like this right here. Because notice I got the x cubed and then the 8x in front. I can factor out a 2, but I also can factor out negative 2. And when I factor out the negative 2, and besides, by the way, let me put that negative 2 inside the integral sign so you can see what's going on here. Integral from 0 to 3. And I'm factoring out the negative 2. If I factor out the negative 2, if I do minus 2x cubed divided by negative 2, that's going to be x cubed minus 8x divided by negative 2. Well, that would be minus 4x. And then dx. Negative 2 divided by the negative 2x cubed, that's x cubed. Negative 2 into the negative x, into the 8x, will be minus 4x. Now I can pull out that negative 2, so it'll be negative 2 times the integral from 0 to 3 of x cubed minus 4x dx, which is exactly this right here. And it's equal to 9/4. So here I have negative 2 times 9/4. Negative 2 is like negative 2 over 1 times 9/4. That would be negative 18/4, which will reduce to negative 9/2. Or you could have did this. This 2 would go into that 4 2 times. You have a 2 in the denominator. Then the negative will make it negative 9/2. So that's part A. Part B looks like this. The integral from 3 to 0 of 4x minus x cubed, 3 dx. Well, I like for the lower limit to be on the bottom and the upper limit on top, so I'll swap these out and put a negative sign in front, so it'll be negative times the integral from 0 to 3 of, also, notice I got 4x minus x cubed. That's almost like this one. So if I want this to be like this, I need to factor out a negative 1. So it'd be negative 1 times that x minus x cubed will be positive 4x cubed. 4x will be minus 4x dx. And then if I pull out the negative, negative times that negative will be positive. So it'll be the integral from 0 to 3 of x cubed minus 4x dx. And of course, the integral from 0 to 3 of x cubed minus 4x dx, that's exactly going to be 9/4. Okay. So that's how we use those value of that first integral I to come up with the other two integrals and what their values will be. All right, so this will conclude this video on section 5.2 dealing with definite intervals. I do have one video that deals with evaluating definite interval using the limit notation. I would do that on a separate video. In the meantime, feel free to reach out to me if you have any questions about anything in this video or any of the homework problems in my math lab.